And that way, we have not yet captured all of our silly conversation before this, but we'll get all the good stuff after.
We'll have silly conversation after this.
I'm honored Ralph's going to join us for reliability and not for exoplanets.
Yeah, I'm here for this one.
Sounds good.
I didn't even realize there were two of these things in parallel. I've been on a Europa Clipper WebEx for the last hour. We're in a lot better shape.
This is early on, Ralph. Remember.
Yeah, you haven't got anywhere near gotten ready to have the problems yet.
Oh no. We may launch this thing before they get that one off the ground.
Ow.
Remember Messenger and Bepi Colombo?
Oh, yes.
Well, let's just keep it simple and we have a chance of launching.
Right.
Yeah. Mention that. I had thought about it earlier, but I failed to mention that in my longevity talk.
Keeping it simple, yes. Don't worry, it's always in my head.
Good.
All right, 2:26. I don't want to get behind too far, so why don't we go ahead and get going? I think pretty much everybody's been on one of these before, so we're going to do it the same way. Please keep your mics muted. It's a smaller crowd for this one than we've had in some of the other ones, so it will be a little bit easier to manage. But still, we want to make sure that Clay is able to give us the information he's got. Once again, use chat freely. I'm monitoring it. We'll make sure that we get questions asked and answered either in real time or as we go along. And if you need to talk to a specific slide or a specific point, raise your hand. We'll try to break into Clay's talk gently so that we don't keep things too off track. And we're going to leave plenty of time at the end for questions and discussion, just like we've been doing. So Clay, I'm going to turn it over to you with that. And I'll be online here, just kind of keeping an eye on things to help make sure that folks' questions are getting through.
Okay. Let's see. Set up here. All right. Whoops. Wrong way. Okay. Hopefully you're seeing full screen now.
I am not, actually.
Yeah.
Yeah.
Did you share?
I have. Hold on a second.
My Zoom doesn't think you've shared.
Well, nuts.
Does somebody
Right, let's try.
Okay, well, oh, there we go.
All right. So there we go. Okay. All right. So talking about the reliability engineering tasks for interstellar probe study. Glenn, in the previous discussion, talked about the larger umbrella subtask on longevity, and reliability engineering falls under that. So you see the team listed here with Glenn and Sally Whitley and Steve Jaskalik. There are others. We have some folks from the University of Maryland Kelsey Center supporting us. You know, obviously the engineering team has a big role to play in what we're doing with the reliability engineering. So with that, we'll talk a little bit about what 50 years means from a reliability perspective. We'll talk a little bit about the historical record and what it can tell us about mission duration, and, you know, does that provide confidence, or how much confidence can it provide that a 50-year spacecraft is achievable? We'll also look at how we're setting up a framework for looking at and evaluating the science requirements and their mapping to reliability, and also then how the reliability of the spacecraft bus folds into that, and then what that overall framework looks like. And then we'll talk a little bit about physics of failure. So one of the things on physics of failure as a methodology to add to the toolbox is we're not going to build and test anything for 50 years and then fly it for a 50-year mission. So we have to have other ways to look at the problem. And here's where the physics of failure can help us. We'll talk a little bit about that towards the end of the talk. So a little bit about the goals as promulgated down through the interstellar probe study into the longevity and then to reliability. So we need to have a spacecraft that operates 50 years or longer. And you've heard from the science discussions and Jim's discussions about where that number comes from and what limitations and constraints that has on other things as well. From a reliability perspective, that's a big change from what we normally do with spacecraft. And I'll show you some data of what design lives look like for spacecraft, at least within the interplanetary realm, and talk a little bit about that. So we have a couple goals for this: identify processes both for the flight system and the ground infrastructure to make sure that we have a successful story for a 50+ year mission. And then also provide information on, basically information on how we can provide confidence to the stakeholders that this kind of mission is achievable. The last bullet there talks about other places where the work we're doing here has impact. So there are many missions that are coming out in the next decadal study that are probably going to require missions that exceed a couple decades, certainly more than what we typically fly in the order of 5 to 10 years. At the same time, the electronics industry is no longer dominated by military applications and the like. Instead, it's dominated by very short lifespan consumer products. And so what does that mean when our engineers pick parts and need to fit within a requirement that is an order of magnitude different than what they're normally used for? Again, looking at the historical record, we'll talk about that. There's other significant trades that can be done elsewhere in the space industry of the trade-off between the longevity of space infrastructure versus tech refresh. Right now, geosatellites, for example, have a 15-year-ish recycle rate. A lot of that is driven by tech refresh. Some of it is just fuel constraints. But if you have the ability to reliably have a spacecraft lasting more than 15 years, double that, what does that do to the discussions with tech refresh? So the point of this is that what we're doing in this study, I think, has ramifications more than just for interstellar probe. So from specifically on reliability, we want to know what it takes and what are the challenges in front of us to make a spacecraft that's going to last this long. And part of this then is also analyzing the baseline design that Jim and the other engineers have gone through in the last couple days. We'll show a little bit about what that looks like, try to identify what those drivers are, and part of what we'll do in the next year then is start to discuss those mitigations and through whether testing or acquisition strategy or whatever to mitigate those kinds of things. And then also part of this is to quantify the uncertainty that we're talking about. It's one thing for us as reliability engineers to go through and come up with a probability number and say, yep, that's the line in the sand, and yes, we can meet it, or no. But there's more information that we need to provide the decision makers, right? What are the assumptions or the impact of the assumptions and the approximations? What are the impacts of the variability of the data, or as we extrapolate far beyond what the testing regime is, what are those uncertainties and how do they come to play? And so all of that needs to be put together in a reliability framework. So can we build systems that last a long time, and certainly without maintaining them? With maintenance, we have lots of systems that last a very long time, very complex systems. Things that are not maintained are harder to find. This picture here of the Oxford bell has been continuously ringing since 1840. Obviously a very small kind of thing here, but it is been in operation for a very, very long time. We also have the experience of the Voyager spacecraft, launched in '77, still operational. Both of these systems were not designed to last this long. So by luck, if you will, we have these things that are operational, and we can look at them and say, okay, what was it that made these work? And easy to jump to the conclusion that, well, we have spacecraft that launched in '77, and therefore we can build spacecraft that'll launch 50 years. There's a couple things on that. This notion of survivor bias that, yeah, we've picked out the ones that have lasted. There are other systems that have not lasted this long. And so we need to look at those as well to make sure we're not fooling ourselves and building the story. Part of what we've been looking at is going through the literature and identifying papers. So there's papers in the reliability literature, specifically for spacecraft. And this one here by Brown is one of those that looks at lifetimes of spacecraft and what that can tell us. There are other places to look in terms of papers talking about Voyager specifically and how they've been maintained and operated and what decisions were made at the time, and a sense of what were good decisions, what were not so good decisions. So there are papers out there like that. There's some papers for systems that are operating as well, like New Horizons. And this particular paper looks at the performance and the very small change in performance of the LORRI instrument, for example. We see similar kinds of things for RTG performance as well, that the performance for some of them don't change over time. So that's good information to know. It's also good information to find the papers and literature that, where there are deviations, what were the root causes of those deviations. So those are the kinds of things that we're looking for just in the general literature. More specific to reliability, the graphs here are excerpts from a couple different papers. The one on the top shows that spacecraft behave in a manner that is not a constant failure rate model. So reliability engineers have a crutch in terms of how we look at electronics and we assume that there's a constant failure rate, and we analyze systems that way. And it turns out spacecraft do not behave that way. That if they have a decreasing failure rate over time, meaning that if a spacecraft is launched and gets through its commissioning in the first several months, they tend to last a very, very long time. And when you start breaking that down as to what's causing that, space is an extremely benign environment. You don't have a lot of vibration, you don't have any corrosion sources, you don't have any oxidation. We tend to keep things at room temperature-ish. Try not to have big temperature swings. So the engineers do a very good job of protecting the electronics, for example, and giving them a nice environment to live in. So after the first energetic kind of events like launch and deployment of arrays and arms and things like that, things settle down. And the data shows that. So this one particular thing is from a report from Liam Sarsfield, RAND Corporation, where he found a lot of this data. He was also pulling data from previous studies that also showed this for spacecraft. Myron Heck's paper from the Rome Air Development Center, for example. The paper at the bottom shows a plot of design life versus actual life. And all the dots there are different kinds of spacecraft. And the red dots are the spacecraft that have failed. And what you see here is that there's a lot of spacecraft that are either still active or have performed well beyond their design life. And what I'll show you in a couple slides is the same kind of analysis just for interplanetary, and we'll start to see the same thing. So yeah. Another set of papers comes out of Georgia Tech, where they have looked at the durations of spacecraft and the subsystems within the spacecraft. And they are finding this very same behavior of decreasing failure rates. They have fit these times and plots of various different spacecraft to a Weibull function. And we see the very same thing with interplanetary spacecraft data as well. And I'll show you that in a little bit too. So to look at the historical record, specifically interplanetary spacecraft, we went to a large data set, this database from a company in the UK that keeps all launches since the 50s. And they characterize many things about the different launches and spacecraft and specifically how they failed. Some limitations on this, because the information they get are things that are in the press. Fortunately, interplanetary spacecraft are things that are in the press, and when things go bad, there's lots of news stories about them, and when things go right, there are lots of news stories about them. So the information there is fairly accurate. But anyway, we have a total data set of 180-ish spacecraft. We took out a lot of spacecraft from that list. A lot of them are very short-lived kinds of things. There are a lot of tech demos, landers, things that don't fit within the long-lived planetary missions that are akin to what we're looking at for an interstellar probe study. And so the data set that we ended up with is around 70 different missions. That represents nearly 700 plus, 725 years of operation. And what you're seeing on the graphs on the side is that most of those are either still active or were retired without failure. And just a smaller subset of them actually failed the mission. Now, some of those have failed after their design life, and some of them have failed beforehand. So it kind of gives you a sense of what is possible with the behaviors of interplanetary spacecraft. The other graph you see at the bottom is how they have failed. And so the red bars that you're seeing there are the failures. The other ones are reasons for retirement. But the thing to take away from there is that there isn't one dominant source of failure for these long duration interplanetary missions. So, there's a number of things for us to keep an eye out and to look after. So I mentioned that there was this kind of look at all spacecraft in terms of actual design life or actual life versus design life. And so this is what that group of 70 spacecraft looks like. And what you see here, the Voyagers at the top, still active, 43 years, and their design life was 4.5 years. You see New Horizons on the other side, that coming up on their design life of 15 years. And you see others smattered through there. And again, what you see here is that spacecraft tend to last a lot longer than their design life. So the next thing to look at from the historical record is a sense of how long these things last. Now, part of the problem with just taking the duration and taking number of failures or the duration time and dividing by the number of missions is that you don't get a good sense of the failure times, because the majority of things did not fail to end the mission. So there's statistical methods called survival analysis that allows us to look at this right sensor data and those observations. So when we start to do that, the analysis gives us a mean duration of all these spacecraft about 53 years. So that's accounting for not only the ones that have failed, but the ones that were retired before they failed and the ones that are still active. So, that's a pretty good indicator that, yeah, what we're talking about is within the realm of possibility. Some caution to be said on this is these numbers here, that's a pretty wide margin of between 40 to 150 years. So the uncertainty that's coming from this, the uncertainty coming from the right sensor nature of the data, gives us this this wide variability or uncertainty of what that number really is. But still, that low end of 37 years is creeping up to what we're looking at. And what you're seeing here on the left side is just the results of a Bayesian updating technique to ingest all the data that we're just looking at. So some caution on this as well. So yeah, the data and the statistics may say that we've got a 95th percentile of 150 years. Layered on top of this are very real constraints on whether materials can last, whether there are wear-out mechanisms at play. And so if these spacecraft haven't reached those things yet and not showing up in the data, then that may be a constraint. And so that's one of the things that we want to be able to break a system apart figuratively and understand the failure modes at end of life and start to test for them. So we understand what those real constraints are way out here. And are we pushing those boundaries? So if those real constraints are around 50 years versus 100 years, we want to know those things. Okay, so a little bit about reliability modeling. We put models together to understand how things can fail. What are those single point failures, if any? What are the impacts of having redundancy? Understanding the uncertainties that I just showed you in the previous chart. So all those things are what we're in the midst of doing with the baseline system. So to give you an overall framework of how we're putting things together, at least right now, we have this structure where, excuse me, we ask questions about and put models together for, does the spacecraft bus fail? And if it does fail within that 50 years, then we've lost the mission. If the spacecraft is working, do we meet all the threshold objectives, or are they lost? And if we have lost the ability to meet threshold objectives, then we've lost the mission. And so there's a logic structure for all the instruments that are needed to meet the science requirements, or the threshold science requirements. And then similarly, there's, you know, if we meet all those thresholds, do we have, you know, the ability to meet all the baseline mission objectives? And if we do, or if we lose those, then we're left with the threshold mission. And if we lose those, or if we meet those, then we have the baseline system. Within each of these boxes, there is a fault tree, another logic model to break those down. And what I'll go through a little bit is how we've put the logic structure for this box, and a little bit about what we're doing with the spacecraft. So I'm talk about the threshold mission requirements box right now. So we start with the science traceability matrix that Pontus has gone over. And we're focusing on those threshold mission objectives and the priority one measurements. And so there's a fault tree constructed, and I'll go through what that fault tree looks like. And so it starts to inform the design team and the mission team as to what potential payload redundancies would do for the system. The success criteria from which we develop this logic model is based on the objectives that are in the traceability matrix. And
Has Clay frozen for anybody else?
Yep, I'm not here.
Yeah.
Yeah, we're not hearing Clay.
Okay.
Same here.
Yeah, so we'll give him a second to see if he can rejoin. I appreciate everybody's patience.
Sounds like a reliability issue.
Exactly. See, he's just demonstrating. He just wanted to be really thorough.
It didn't last 50 years.
The general issue is if it lasts for a few years, it'll last and last. We haven't got to the few years yet.
Yeah, that's for sure. So since he stopped sharing, I'm assuming that means he's trying to restart everything. So I'm hoping that he'll be back soon. In the meantime, we can all look at Gabe's awesome background in the Explorers Club.
Don't we all want to be back there right now?
Yes, I do.
Not
Badly.
in New York City, I don't.
This time next year.
Well, it's simple. Never leave the club.
That's true.
I'll take the couch on the 5th floor.
Okay, well, this could make for an interesting presentation. Glenn, are you prepared to take over?
Did somebody text him? Maybe he's still speaking.
Well, he left the meeting, so I'm assuming that means that either his Zoom application quit or he figured it out.
I think I saw him try to rejoin too. Maybe I'm seeing things, but I think he knows.
So too.
I have had Zoom totally crash on me before, and sometimes I've had to actually reboot my computer to get it to work. So.
Okay, so we need to think of some really hard question for him for when he comes back.
What do we do if Apophis is going to strike the Earth in 2068?
There we go.
Let's hope he comes back. I'm supposed to be on another meeting here in 5 minutes, so.
Okay. Okay. Well, I mean, if Clay doesn't come back here soon, we'll try to. I don't know, Andrea. I don't know if we can reschedule or fit this in somewhere else, or try to catch up some other time. We've got a pretty full schedule, I think.
We do have a pretty full schedule. What we could do is record Clay's talk and then facilitate conversation asynchronously using a Google Doc.
Yeah, that's a good idea.
So,
Yeah,
I'll call us. What's up?
we're about halfway through his talk.
Right.
There you go.
Here he is.
hey!
Not quite back yet. Nope, there he is. Cool.
Sorry about that.
Oh, welcome back.
Where was I?
About halfway.
All right.
Okay. Left
am I
off.
sharing?
No, not yet.
Not
You
quite
had about the.
Like 17 or so?
Huh?
Yeah, I think slide 17 is probably reasonable.
Yep.
Yep.
As you know, the chart just before that when he died.
Okay. All right. Okay, so a little bit about what the fault tree will show you. This is done in failure space. So when we talk about AND gates and OR gates, this is in failure space. I know that a lot of the logic designers don't look at it this way, but you know, this is the tool and the application in the reliability world. So just to set the stage. So what I've done is to take each of the measurement types that are laid out in the traceability matrix, where we have the goals, the objectives, the questions, and the measurements. And for each one of those, there's a series of dots that have been identified by the science team in terms of what instruments are needed and in what phase of the mission, and if some of them are primary and secondary to each other. And so this sets up a logic structure for us to look at, in this case, you need MAG, PLS, EPS, CRS, and either ENA or high or medium. Also, what you'll see is that for this particular one, you need these instruments in phase 2, but they need to have survived phase 1 in order to be here in phase 2. So you'll see that structure come across as well. So we take these dots and we start to form the fault tree, starting at loss of science, having to meet the science objectives. And again, you need to answer. Question? Okay. You need to answer 2 of the 8 questions. You need to answer at least one question, and then one of the priority one measurements. And then within that, in order to meet the measurement, you need, in this case, MAG, PLS, EPS, CRS, or a combination of high and medium. Okay, so this is how the fault tree itself is breaking down. And one more layer to that, like I mentioned, is that you need these to operate in phase one in order for them to operate in phase two. So where we have loss of MAG, for example, it needs to succeed through phase one and phase two. Or in a failure space, if a failure of MAG in phase one or phase two means that you've lost the instrument. So when we start taking that structure, at least for this one example, and then saying, okay, what are the combinations of failures that can cause loss of that particular line item, loss of MAG in phase one or phase two, PLS, EPS, etc., or combination of high and medium in various phases. All of those will get you to loss of that one item in the traceability matrix. Now, when we roll that up for all of the questions in the matrix itself, what we end up with is these three single point failures: MAG in the first phase, or MAG in the second phase, or MAG in the third phase. There are a number of double combinations of, in this case, high in the first phase and PLS in the first phase, et cetera, et cetera. There are a number of combination of triples and on from there, of combinations of 4, 5, et cetera. And all of these combinations of things will give us a loss of threshold mission. So one of the things that you can see from this is that since the MAG is a single point failure here, putting a redundant magnetometers on there would help with that. Now, the next part of this is it's not enough just to look at the instrument itself, but as we do more and more investigation, as the design matures more and more of the instrument suite, and how they're connected to power, how they're connected to data, how they're connected mechanically, fields of view, all the other dependencies that happen on a spacecraft, you may get more or less of these combinations of things that can go bad. Just as an aside, this is the same process that we use for Parker Solar Probe. And what we had in that case is that there were 3 science objectives, and there were 3 questions within each of those objectives. And success was determined as needing to answer 7 of the 9 questions. And as we started to look at this and how the mapping between instruments and sensors to the requirements panned out, we didn't find any single point failures of the sensors themselves. However, what we did find was that the power supply within one of the instruments was a single point failure. Wasn't a single point failure per se to the sensors, but it did take out enough of the combination of sensors across multiple questions that raised it to a single point failure. And so the design team was able to look at that and come up with creative ways of splitting the power supply, so we no longer had that single point failure. So those are the kinds of things that we can do with this analysis. So it's not just as a planning tool for which instruments can be redundant or functionally compensate for others, but also when we start digging into more of the details, what is there to find. We do a similar methodology for the spacecraft bus. So here's a representation of the block diagram for the spacecraft. And we break that down to, okay, loss of the bus for avionics, GNC, power, et cetera, and within each one of these, there's a fault tree that describes the system itself. Down, eventually, during a development program, what you would have is things down to card or component level, depending on the level of program. So what we have done is taken things down to at least the functional block diagram for the system. And here's an example of what the telecom system looks like. And Dave has probably gone over the diagram here. Lots of redundancy in here. As we do that same kind of analysis, there are some single point failures in here. So the antenna themselves are. You've got these combination points here that show up. They tend to be passive, and so the probabilities aren't going to be an issue. And then there are the hybrid itself. I think I pointed out one there. And the baseball switch itself show up as single point failures. And then there are lots of other doubles and triples as well, but you start to see that combinations of failures can get you to loss of the telecom system. And so it's looking at this is feedback back to the engineering team to say, yeah, this is what we can do, or we can mitigate these, or come up with the story of how they're going to be mitigated. All right, so talking about what's different in a mission that needs to last 50 years. So the kinds of things I just showed you with the fault trees are done typically with spacecraft, but we need to start looking at what are those probabilities of failure that are outside our experience set and outside what we can normally test. And there are going to be a lot of uncertainties associated with that. So what you're seeing here is how normal deliverables and analysis get rolled in. So failure modes and effects analysis or criticality analysis is typically done. Fault trees are typically done. Probabilistic risk assessments are typically done. This understanding of how things can fail at the end of life is something that we need to insert. So the failure modes and effects analysis will identify what those failures are and what the modes of failures are. We need to start thinking outside our normal sphere of experience and look at end of life. We need to then start to look at what those physics, those mechanisms, those degradation, those aging mechanisms that are occurring, and understand how we can test for them. And that testing then will start to inform our view of the uncertainties as we extrapolate out. It will also allow us to say, what things and parameters of the physics do we really need to understand in order to provide confidence at the back end? So this tie to risk-informed testing, and therefore the testing recommendations, is something that is going to be inserted into a development program for something like an interstellar probe. And it's all related to not just understanding what typically fails, but how things can potentially fail 50 years after launch. What this chart is trying to say is that we want to move away from a reliability program that relies on looking at data, counting failures and hours and dividing them to come up with a failure rate, but actually put together a view of the world that can be updated with various statistical techniques and get to a point where we understand what the the uncertainty distribution of the requirement, how can spacecraft last, and what the probability of meeting that requirement is. And this is not just for the spacecraft, but the components and the systems, and then aggregate all that information back up. So the physics of failure modeling, talked briefly about it, but there are things that we want to understand and give us some concern. So general electronic component, the circuit boards, the interconnects, how will those components, parts act over time? And talking with folks, say, from Goddard, provided us some anecdotal stories about part degradation from Hubble. So they have returned, or did return, some components that were on orbit for close to 20 years. And they saw some disturbing things in chips, for example, that how they described it as metal being eaten away in traces within the chip itself. We'd like to understand that. Is that a physical limitation? Which brings up a point that also concerns us, is we can go through and say, okay, we looked at Voyager, for example. It's lasted 43 years. And so there's that as a benchmark. That is 1970s technology that's flying. So do the lessons learned that we take from looking at 1970s technology apply to 2020 technology in terms of, let's say, IC feature size or material manufacturing processes, et cetera, et cetera. So there's some transformation function that needs to be looked at and fully understood. Components for high voltage circuits are of concern. How do they age and degrade over time? The RTGs the technology is changing, has changed somewhat from what Voyagers are. And so what does that change in technology mean for the lifetime of RTGs? And we can have the similar conversations for sensors and detectors and thrusters, et cetera, right? Thrusters, for example, are going to be moving parts. And so what does that mean in terms of, constantly or continually moving throughout a 50-year mission? Oh yeah, the one point at the bottom here, the Kelsey Center at University of Maryland looks at these kinds of things, and they have lots of labs set up to push on research here. So they are helping us in trying to identify and at least scope these problems, and at least identify what the top concerns for electronics and power systems should be. This is to indicate that while most of what I've talked about is hardware related, that the robustness of a mission is not just the hardware. Some of it is the longevity issues that Glenn Fountain talked about earlier, but it also goes into how the fault management system is designed, and what kind of autonomy does that have, and what is the reliability of the autonomy system in and of itself? Can we design the systems to be functionally redundant to each other? Can a processor in one system be reprogrammed to take over for something else that has failed? Not sure how all of that is going to fit within the baseline discussions that are going on, but they are questions to ask. How artificial intelligence, either on board or on the ground, play within this, and can it help with the reliability aspects of a mission like this? So those are questions to be addressed in the coming year. They're on our plate to do. So I want to end with this set of questions. So we're trying to engage the community at large. So if there are data sets that we haven't addressed and should be looking at, we'd like to understand what those are and engage with them. Understanding physics of failure in the space environment. So if people know of research and data that is ongoing that would apply to the kinds of problems that we're identifying, then we'd like to hear from that as well. Any of the previous missions, certainly the ones that are highlighted on that actual versus design life chart, in terms of what lessons learned and how they're continuing to operate and things like that, we'd love to hear from as well. And you know, one of the questions I'd like to end with on some of these things is, you know, what am I not asking that I should be? What else is there that isn't covered right now that we need to you know, put on our radar? So yeah, that's what I have. And so I'd like to open it up for questions and turn it back over to Jim.
Great, thanks, Clay. I didn't see anything in the chat that people have asked already. So I think we're just ready to open it up for folks to turn on their mics and sling away at Clay, and let's see what kind of suggestions and questions and comments we have. Okay, well, Clay, I'll start out. So you mentioned that we're taking an approach, the approach that we're taking on Parker Solar Probe. How successful are we with what we have so far in trying to do something similar here? Do you think that we have really kind of broken things down so that we can make some recommendations to the science community about how to build a more robust payload?
I think we have a good step going forward. I think one of the things that we were able to engage with the science team, and we haven't yet done, is what those functional redundancies or overlaps in measurement types from the different instrument suites can or should exist in order to provide that kind of functional redundancy. And so some of that is analytical, that you need to have derivative information from other instruments in order to supplement something that is gone. You know, it's another couple layers deep in where we are at the moment. But as the interaction with Pontus and the team, I think we're well on the way to doing that.
Yep, sounds great.
This is Ralph. So have you considered a multi-tier approach to reliability, where maybe things within the known, they say for the next 20, 25 years, we know that, score that, and try to bring our primary science into that realm, and then score it differently for the ones that are further out in the mission, going out to 50 years? I'm not sure if that adds value. I'm just asking a question. So.
We have not done that. So I guess what you're asking for is kind of a weighting factor on where the science is coming from. But I think that is baked into the success criteria that Pontus has laid up, in terms of you need to be able to address, you know, two of the requirements or questions. And he has things that are separated between the threshold mission and the baseline mission. So, you know, what I showed you was only the threshold mission. As we go through and actually do the baseline things, I think a lot of what you're asking for will fall out. So I think the structure is laid out already to do some of that.
Okay.
Yes, so just so I understand too. So do you mean that you would wait it, meaning that you would not turn on instruments until you reach a certain phase, Raphael?
No, if you knew you had a really high reliability up to a certain point, maybe you try to bring that science, within that realm so that you have a certain probability of success. And after that point, you might have to do certain things like maybe power off the instrument afterwards just to increase that probability of success after that threshold is achieved.
So you mean you sort of bake it into the operations of the instruments?
Yeah.
Right.
Another way you can think of it is sort of thinking of it in the opposite direction, which is if I know I have an instrument that has a high probability of making it for 20 years, just to pick a number out of the air, right? And Clay, is there a way to incorporate that in the analysis so that for that first 20 years of the mission, you have pretty low uncertainties in your reliability estimate, but then that uncertainty grows as you get further and further away from that sort of known realm?
Yeah, that's exactly what will happen, is that the testing regime will bound where we have information for. The historical record will also help with that. And then things outward are extrapolation outside your data set. So yes, the uncertainty does need to grow for that. If the uncertainty is to the extent that it is unacceptable risk posture to the decision makers, then that's feedback back to the testing program to say we need to understand further out in order to collapse that uncertainty.
Mm-hmm. Okay, so that's where you're looking at risk-informed testing, right?
Right.
Okay. Can you talk a little bit about how we're communicating with outside organizations on this? I mean, you mentioned CalC. Are there other areas? I mean, there are other organizations dealing with these same problems, right?
Yeah. So we've been engaged with NASA writ large. The reliability fellow at NASA headquarters, right now it's Nancy Lindsay, is supporting us in looking at these things and making contacts for us within various parts of NASA. So we have had discussions with JPO and their reliability team. We've had discussions with Goddard and their reliability team. So not just the reliability in terms of the modeling aspects, but the people who are looking at parts and those programs as well. We've had discussions with the NASA statistical engineering team, and we have more of that kind of interaction set up with the larger NASA reliability team. We have made some inroads talking to, say, the GPS program office. They have very long-lived spacecraft as well. Part of what the research that they're pushing on is battery technology, trying to get them out to batteries that are lasting 20 years for their use case. So yeah, we are pushing out and talking to a variety of different folks.
That's great.
I know Glenn, Steve, you want to weigh in on that?
So I'm not sure Glenn is still here.
The one thing I'd add is we're going to be looking in particular about things where historical methods of pushing reliability testing out, such as accelerated testing with high temperatures or high stress voltages or whatever, unfortunately compromise some of the aging techniques that we're particularly worried about. And so there's a limitation on how much you can extend that testing realm for accelerated testing and so forth. And we don't have the answers, but it's one of the things we need to better understand.
Mm-hmm. Yeah, it strikes me that this is a problem that NASA is going to want to deal with, not just because of this mission, but for, I know that there are a number of missions on the table that would be longer than sort of the 15-year lifetime, which is kind of the upper bound for deep space right now that we've, intentionally designed for.
Right.
So I know there one thing that we have discussed that come up is a scary thought, and that was I think it was electron migration, increased electron migration and tunneling for integrated circuits. Is that something you want to elaborate on for the audience?
Well, it's outside my expertise. It was just concerning that the Goddard folks were seeing this. So that's one of the places where, as Jim was asking about interaction, we still have to plan a second meeting with those folks at Goddard so they can present more of the data that they got from their Hubble experience. Like to push on others that may have returned equipment from orbit. So possibly talking to Johnson Space Center to see, if they are seeing the same kinds of things on equipment that they're returning from space station. Right, space station was launched late 90s. I'm not sure how much of the equipment is rotated back down, and if they have things that have been up there for 2 decades, are they seeing things? So yeah, it's in terms of the specifics of that failure mode, I'm not the right person to ask. I don't know, Steve, if you want to say more.
Just briefly is the fact that, as you mentioned, we have to be careful about extending experiential knowledge from Voyager and older missions where feature sizes were 5 or 10 or 20 microns and so forth on transistors, and the metallization was larger just because that's all they could build, to what we have now with sub-micron sizes and very thin metal tracks and so forth. So we're going to have to look at that. That's what Goddard was talking about, and even that was more robust technologies than we've got now. And that's where Kelsey comes in to help us with some of that.
Yep. So what's the possibility that we might be able to, I'm going to say, go back to some of these other technologies and still maintain some reasonable performance in electronics? Are there places we can go to build devices in some of these bigger technologies that might be more robust to the aging effects?
Yeah, that's one thing that Glenn was pushing on, that as a larger question for NASA, if that is something that needs to be done and foundries set up specifically to do this, then that has to be part of the planning and thought process for something like a multi-decadal mission. The other thing that comes along with that then are the property rights to go with that, right? So if a design is no longer being produced, will that manufacturer then allow that to be reinstated under some other ownership, right? Good questions to ask, and not easy problems to solve, I would suspect.
Yeah. I mean, there's a real design discipline problem here as well. It's the hardware side of, or the hardware equivalent to coding in Fortran.
Yes.
We now have an entire generation of engineers who are used to being able to design in certain technologies. Our radio counts on having a 4 million gate array FPGA. Mm-hmm. If we have to go back in technology, these simply are not available.
Yep. Yep, that's exactly true. Any other questions for or discussion for Clay in the reliability subject? Ralph is asking privately, I'm going to say anyway, no 5U4 rectifier tubes. As a guitar player, I appreciate the whole tube conversation.
Guitar amps and spacecraft is where you still find them.
That's right. All right, so it's essentially 3:30 at this point. We're scheduled to end at 3:40. I don't know whether there is another plenary session on our schedule for folks to wrap up today. It doesn't look like there is. One last shot. Mm-hmm. Go ahead.
Hey, Jim, before you let everybody go, I was just curious. It looks like there's several people out there that are from some other technical organizations. I don't know if any of them would like to volunteer to speak up and say whether this was old hat, this was new to them, this is interesting. Any volunteers or any takers before Jim shuts this down? Maybe not. Oh, well, I tried. Back to you, Jim.
Well, this is Bill Niesper from JPL. One of the things that I'd like to add is that certainly what you described in terms of tracking failure mechanisms and understanding that was something that actually we followed to get the GPHS RTG, prior to that, the Voyager RTGs. And of course, that tracked back to LES 8 and 9, but the types of testing, understanding what was going to break, how to simulate it, test it, how long to test it. And certainly we couldn't test it for the 43 years that the Voyagers ended up flying for, but that worked very well for us. And the culture there was one of track and understand failure mechanisms on the RTGs, in particular the thermoelectric converters were the real driving technology there. And in essence, that's the technology we're talking about using in this system too.
Yeah, one of the things that changes is the culture of testing under what you were just describing, testing to failure to understand how things break, as opposed to test to make sure that it's not going to break during the mission. And so when we're looking at things that are 2-year missions, 5-year missions, right, the testing is, yes, it's working. We don't tend to take things and break them and understand why. But that is what's going to happen for a lot of these kinds of systems and components, is understand how they are going to break.
One of the challenges that we had was that to try to accelerate the failure, we tended to raise the temperatures. But we had to be careful that we didn't raise the temperature so much that we introduced a new type of failure mechanism that didn't really apply to the RTGs with the kind of temperatures that they would actually be exposed to as a result of the heat source that we were using.
Yep.
Yeah. One of the other things that the people at Goddard pointed out is that if you raise the temperature on some of these things, you tend to anneal the part and therefore prevent failure mechanisms from happening, the ones that you wanted to see at aging and end of life. And so, you have this, both of those problems existing in the testing process.
We ended up doing a lot of materials testing and then doing the destructive physical analysis and then looking at it closely and seeing how, for example, in our case, how the chemistry migrated within the system and how stable it was, and if there were intermediate layers that were formed that created a certain stability, particularly in all of the joints and junctions and things that we use to bond them together.
Yep, absolutely. Okay, is there anyone else out there that'd like to share about this? Any other experiences that would be helpful? Okay, we will certainly continue to reach out to other organizations. I know that's in the plan for the rest of the study. So before we go, I did want to mention a few things. First of all, remember the Google Docs, especially the one for this session. And if you scroll back in the chat just a little bit, you can see the link for that. Again, if things occur to you after the fact, we're going to continue to monitor those Google Docs, and we'll continue to take inputs and have conversations through that. As for tomorrow, starting at 10 o'clock, we're going to have the welcome and overview again. And then shortly thereafter, there'll be a science track that's going to cover particles, astrophysics, and dust. On the engineering side, we're going to be talking about the communication trades that that Reza will be sharing with us. And then we have a session on that will briefly mention some over-Earth maneuver concerns and then update folks on the materials testing that they've been doing. And then we'll end up with some guidance and control thoughts from Gabe. And then that'll be tomorrow. And again, we'll have Google Docs for all of those as well. And with that, I'll open it up for any last comments. Anybody want to jump in and
So there's one from an early career from Eric in the chat.
Great. Did I? Oh, I did. I recently graduated with a mechanical engineering degree with some coursework in aerospace. Found all this very interesting. The purpose in designing a spacecraft is not the same as something you will remain near the ground. And hearing it from you all with the intent to do this, all the planning, I have a little more than the ability to understand the things you're saying at this point in my career. But thanks for the opportunity to listen. And you know, the thing that Eric and all the other folks who are beginning their careers need to realize is that, once again, as we said in the previous session, you know, we're doing this for you because, you know, the folks that you see here at the top of the screen who are leading this thing, we're not going to be around for probably even the very beginning of this mission. Most of us are probably within 10 years of retiring at this point, and we certainly won't see the end of this mission. So you know, we are sensitive to and want to maintain communication with the folks who will really be running this mission, right? And so, Eric, I appreciate you coming and listening to what's going on, and I hope that you'll stay involved with us.
Yeah, absolutely. And there's a lot to do. And Jim is right. There are several of us within 10 years of retirement. I'm actually on the other side of that, and which is a different problem. But when I was a graduate student, I got to watch Voyager 1 launch, and I've been involved with Voyager ever since, and with all of this. And so, again, Eric, welcome. We'll have work for you to do later on.
Sounds good.
Yes, starting actually tomorrow. So I maybe planned already, but the 9 a.m. session, that's for early career.
Absolutely.
And we have to get some good ideas out of you.
That's on Friday. Tomorrow's Thursday.
Tomorrow's Thursday. It's only
Friday.
It's only Wednesday.
And it's been a long day today already.
That's right.
I need another cup of coffee.
All right. So with that, I'm going to open it up one more time again. Is there any other comments that we want to have here? We've got just a few minutes left, and then we'll go ahead and call it a day. Okay. Well, thanks everybody for coming out. I'm going to stop the recording, and we'll see you tomorrow.
See you tomorrow.
See ya.
Thank you. Bye-bye.
Bye, everybody.